my name is Elahe Soltanaghaei from Carnegie Mellon University, and today I'm presenting our paper on developing an ultra-low power Wi-Fi tag that works with existing Wi-Fi infrastructure. In a smart world, there are many things that we want to find that are not powered, such as a bottle of pill or a package in a warehouse. RFID is specifically a technology developed for tracking and identifying objects. There's a battery-free tag like a barcode that attaches to the object. It receives the signal from the reader and reflects back a modulated version of it. However, because of the deployment complexities, we don't really have RFID readers in every building. So we asked, what if we design a tag that can be detected and localized with any Wi-Fi connected device? Nowadays, we have free Wi-Fi almost in any building, like homes, restaurants, hotel rooms. So you can imagine having these tags attached to your wallet, keychain, tools, toys, and then you can just use the Wi-Fi in the building and your personal Wi-Fi devices like phone or tablet to find them. However, the main challenge is that the tag reflection is multiple times weaker than the line of sight or other reflections in the environment, causing a high dynamic range. This is problematic specifically in Wi-Fi setups where we have separate Wi-Fi transmitter and receiver and no time synchronization between them. Other papers on Wi-Fi backscattering solve this problem by designing a tag that reflects a frequency shifted version of the received signal, so it won't interfere with other multipath signals. But this requires the transmitter and receiver to operate in different wireless channels, and that's not how Wi-Fi networks work. The whole idea here is to piggyback tag detection on top of ongoing Wi-Fi packets. So the main questions we're trying to answer here are, how can we backscatter ambient Wi-Fi traffic without modifying the normal operation of Wi-Fi networks, how we can overcome the dynamic range problem and separate the tag reflection from other multipath signals, and finally, how to locate the tag from a single receiver like your phone or tablet. First, we propose a fully asynchronous tag reader architecture where we separate the source of power at the tag from the backscatter signal we use for tag detection. We design the tag as simple and low power as possible that it can constantly be on and modulate any received signal. Then the Wi-Fi devices start their normal communication and the tag independently modulates the reflection from it. The receiver then captures the signal measurements in the physical layer known as channel state information and searches for the tag reflection. So all we need at the tag is an RF switch and a Wi-Fi antenna. When the switch is off, the received signal will be absorbed by the load attached to the antenna, and when the switch is on, the antenna will be shorted and all the received signals will reflect back. And that's how the tag is communicating with the reader, sending 0-1 bits by switching on and off. But how can we separate the tag reflection from other multipath signals? To answer this question, let's start with an analogy that explains the high-level intuition. Imagine you're out in a dark night and all you can see is some weak lights in distance that you may not even notice. However, if one of these lights start blinking, it gets your attention. And that's basically the intuition we're using to detect a very specific reflection from the tag in a signal processing pipeline. So the blinking in the previous example is basically the modulation of the tag reflection across packets. But pay attention that because of the asynchronous architecture we talked about earlier, we don't really know when the tag is switching on and off. So to extract the tag reflection, we use a super resolution algorithm that takes measurements of the signal from multiple packets and combine them together to estimate the parameters of all multipath signals, including the tag reflection. But why does it work? Please refer to our paper to find the answer to this question and many others on tag discovery. By the end of this phase, we have the tag detected and we estimated its angle of arrival, angle of departure, and time of flight parameters. Now let's see how we can locate the tag from a single point. Here, all we need is the direction and the length of the reflected path and the line of sight between the Wi-Fi devices and the tag to form a triangle and solve it for the tag location. So instead of using multiple receivers for triangulation, we are using the multipath reflection from the tag to form this triangle. We implemented a TagFi and with multiple prototypes using off-the-shelf components as well as an integrated PCB with a custom designed patch antenna. We developed a localization system on top of it and tested it in 100 different scenarios in the lab and a large arena space. And we see that we can achieve a median accuracy of about 30 centimeters to locate these tags in the 2D space. We also develop an augmented reality interface that collects the wireless signals and locate any number of active tags and show it to the user with an AR overlay. Here's another setup with multiple tags, and as you can see, we can detect and localize all of them at the same time. Each of these tags have a different modulation rate, and that's what we are using to differentiate them from each other. So to summarize, TagFi is an ultra-low power Wi-Fi tag that is compatible with the Wi-Fi networks in any building. To find the objects, we can use any Wi-Fi link in the building, and such an approach can evolve wireless medium into an intelligent sensing platform in more environments.